Okay, welcome everyone to the afternoon session. So we're extremely happy to have next speaker, Corinne Yap from Georgia Tech, who's going to tell us about spin models on random regular graphs.
Great. Hopefully everyone can hear me. Yeah? Okay. Thanks so much, Rob, and also Guillermo and all the organizers for a really great summer school so far. It's really great to be able to be at IMPA and in Rio for the first time. So I am going to give this talk in maybe an opposite way that I usually give talks like this. Normally, I give some motivation for the problem, and then I say the problem and our results, and then I say how we prove them. I'm going to do the opposite of that and instead introduce some interesting objects that are in the intersections of combinatorics, probability, statistical physics, maybe some questions you might want to ask about them, some tools that we have to study these objects, and at the very end, I will say some results about them and what we proved. So it won't be until the end, but the results that I do discuss will include joint work with two groups of people, including Reza Gaysari, who's at Northwestern, Aya Kuchikova, who is a graduate student at Georgia Tech, Marcus Papik, who is a graduate student at Potsdam in Germany, and Will Perkins, who's also at Georgia Tech. Okay, so let me start by just introducing the general flavor of problem that I want to consider and that I'm interested in, which is a word that maybe you've heard of in different contexts. It's about thresholds or phase transitions. And these mean similar things, but to different people in different contexts. So what do I mean by this kind of broadly? If I say the word threshold, then if you're a probabilistic combinatorialist, this type of question might be the first thing that you consider. So we've seen actually this question before in Matthew's talk, like what's the probability GNP contains a triangle, where GNP, of course, is the Erdős-Rényi random graph, where I have n vertices, and each pair of vertices independently forms an edge with probability p. And so I actually had a high school student model this in SAGE, and he sampled on 100 vertices. He approximated this probability for several different values of p. And what can we observe about this plot, this experiment? We can observe that for small values of p, the probability looks pretty close to or identically 0. And that should make sense. As we have very few edges, then the probability of containing any triangle should be pretty small. But as p sort of jumps past a certain range, suddenly the probability jumps to 1. It becomes very likely for us to have a triangle. But there's something interesting happening in the middle here where there is this growth, sort of sudden growth from probability being 0 to probability being 1. And if you actually sit down and try and answer this question explicitly, you'll see this is not just sort of a result of some experimentation. This is actually the truth. We have what's called a threshold here with respect to p for this property containing a triangle. Okay, so that's one example of what you might think of as a threshold in a random graph. But if you come from the world of physics, then you might think of a different sort of question when you ask about phase transitions. So I took this from a WikiHow page that tells you how to demagnetize a magnet. There are several suggestions on that page. A lot of them are not good suggestions. Some of them are like hitting the magnet really hard. But this one actually works. So if you take a magnet, not quite a fridge magnet, a magnet with no like plastic on it or anything, and you hold it over a flame, you'll see that as the temperature of the magnet increases, it will at some point lose its magnetization property. It will fall off the fridge. And that is another example of, in the physical world, some sort of phase transition happening, this time with respect to temperature. So somehow the structure of the particles in the magnet are changing in some sense with respect to this temperature parameter. Okay. So the type of question I'm interested in is studying these types of thresholds or phase transition behaviors from both the combinatorial and the statistical physics perspective. And I'll just broadly describe this as the existence of some critical point marking a change in typical behavior. And the two examples we saw so far are examples of what you might call a structural phase transition, right? What is the structure of a typical configuration? But there are other types of thresholds we could study. In particular, you could study something like algorithmic thresholds. Do there exist efficient algorithms for sampling from a given probability distribution? Or a dynamical threshold, right? How quickly does some sort of evolving process approach its steady state? And how does the speed of this evolution change as we change certain parameters about the process? And so these are the main types of questions I want to consider, and now what I'm going to do is give you an explicit example, and we'll see how these, the answers to these questions kind of relate or don't relate to one another. Okay, so let me start with sort of the first third of my talk subtitle, which was magnets. Okay, magnets, moments, and mixing. Those are the three main sections of the talk. So first of all, magnets. What I mean by that is the Ising model. So it wasn't an accident that I chose this WikiHow article on how to demagnetize a magnet. What is the Ising model? Well, it was developed by physicists as some way to model like the actual structure of magnetization. So one way you can think of a magnet is that you have a bunch of particles arranged in space, let's say in some very nice geometric configuration like a lattice. And each particle has a positive or a negative spin associated with it. So we can think of that as like having these nodes on this lattice, and each is carrying a plus or a minus symbol next to it. Okay, but as combinatorialists, we know what this secretly is. This is a graph. And these pluses and minuses, well, we don't actually care about the physical meaning of the plus or minus. They're two different colors. They're two different labels. And so what the Ising model is simply a distribution on what I'll call spin configurations, which are just two vertex colorings of my graph. Now note, I'm not talking about proper colorings, right? I'm not specifying that edges don't have the same spin at both endpoints, and that will be sort of a main point here. I'm just considering all possible ways of assigning the vertices of some graph to the two colors, +1 and -1, or if you like, red and blue. And so we're going to consider this model as defined by this probability distribution, which I'm calling mu, and we don't have to stick to lattices in the, as motivated by physics. We can consider this model on any graph. And what is this probability distribution? Well, I'll tell you what it is, but first let me tell you it does have some parameters since it's going to represent this physical process. Beta is going to be what I'll call the inverse temperature, and lambda is the external field. So I'm going to keep a board of notation here. So it won't be so important right now to remember all of the notation, but in case you want to reference it, I'll keep it on this board. So beta is the inverse temperature. Lambda is the external field. And sigma will always be a spin configuration, or two coloring. Okay, now let me tell you actually what this probability distribution is. So I'll say the weight of a two coloring is given by this expression here. So it's e to the beta times something, and then times lambda to the something. So this e to the beta, the mg sigma there means the number of monochromatic edges in my coloring. So that's the number of edges with the same spin at both endpoints. And the sigma plus is the number of +1 spins in my configuration. Okay, so the Gibbs measure, mu of sigma, I'll have my weight times number of I'll abbreviate this monochromatic edges, lambda to the number of +1 spins. Okay, and okay, what do I mean by this funny proportional symbol here? What I really mean is that the probability of a configuration is equal to this expression divided by some normalizing constant, which is the sum of all the weights. So this should look familiar if you saw Matthew's talk, right? This is sort of the format of the Gibbs measure that he introduced for the hardcore model on Monday. Okay, and so let me just say this is over CG beta lambda, CG beta lambda. This is the sum over all sigma. Which is the partition function. Okay, so it's not so important that you remember exactly this expression. What I want to do instead is give you some intuition for why this is like the correct probability distribution to study. I like what Matthew said yesterday, which is statistical physics is really the business of analyzing weird probability distributions. Like, how do we analyze this? Why is this something that you might want to come up with? Okay, so let me get some audience participation here. So I've reminded you of the definition up here as well on the board. Let's try and understand what is going on with this distribution, right? I said it was modeling something physical. Why does that make sense with this expression? So let's forget about lambda for now, this external field. It's giving some sort of bias. Let's just set it equal to 1 so we can ignore it. And let's look at this e to the beta times m parameter. So the distribution is going to change based on what my parameter beta is. So let's first think about the regime where we have small beta. So let's think of beta tending to 0. Can someone tell me, someone who hasn't seen me give this talk before, when beta is tending towards 0, what is the distribution mu? Uniform, thank you. This is a uniform distribution. Why? Because if beta is tending to 0, then this exponent, e to the beta m is going to be tending towards 0 no matter what the number of monochromatic edges is in your distribution. So everything will have weight 1, regardless of what it looks like. And so that's going to be the uniform distribution. And we can see sort of an example of that in this picture on the left. So what I've represented here is a subgrid of Z2. Really, I'm looking at the dual of Z2. So every tiny grid square I'm thinking of as a vertex. And each grid square, its neighbors, its edges, are to the 4 nearest neighbors of that grid square. And so that's determining my monochromatic edges. And you can see that, as we're at small beta, there's no particular structure that's being biased towards. And things look pretty disordered. And why might that make sense? Well, if we're at small beta, I said that was inverse temperature. So you can think of that as 1 divided by temperature. Then small inverse temperature is high temperature. And what do we expect of physical systems at high temperatures? We expect them to be gaseous or disordered. So this makes sense as a probability distribution to describe that physical system. Okay, on the other end, what about large beta? So if beta is tending towards infinity, what is my probability distribution mu? In particular, what am I biasing towards? What's most likely to appear in this distribution? Yeah, clusters are all monochromatic. In fact, if I take beta tending towards infinity, then this distribution will be uniform on the configurations that have the maximum number of monochromatic edges, and that will be the 2 all monochromatic ones, all purple or all blue in this case. So as beta is very large, we're tending towards being dominated by 1 color. And why does that make sense? We're at large beta, which is low temperature, and so we expect things to be sort of solid-like or in some sort of ordered state. So, okay. So I want you to keep this in mind as sort of what this distribution actually means. We're sort of we have this difference in structure. We're at small beta, we're sort of disordered, and at large beta, we're somewhat ordered. And we can see just by definition of the model, we have some sort of structural phase transitioning happening. Phase transition happening. All right, and then let me just mention why I'm including this lambda parameter, because sometimes you'll see definitions of Ising model that don't include the external field. So this will be very important for sort of the actual results that I state later. And what is this lambda doing? It's simply biasing either towards or against having more +1 spins. So if lambda is greater than 1, we're biasing towards having even more of one color than the other. Okay, but let's look at the other types of phase transitions that I mentioned at the beginning of the talk. Let's look at algorithms. So I won't say much about this because sort of the question of algorithms for the Ising model is sort of a resolved question. For about 30 years now, we've known that actually for any choice of graph, for any choice of parameters, beta and lambda, there exist efficient approximate what are called counting and sampling algorithms for the Ising model. So what that means is approximately sampling from the distribution mu, and counting refers to estimating this partition function, z. And those questions for the Ising model go hand in hand. Okay. So let's now look at the last type of threshold that I mentioned, which was a dynamical threshold. And that actually, in some ways, relates to this algorithmic threshold, as we'll see. What do I mean by dynamics? Well, you can define a Markov chain that will give you the Ising model distribution in a very simple way. Start with some two-coloring on your graph, then just pick a vertex uniformly at random and recolor it. But you want to recolor it with a particular probability, and the probability you recolor it should be conditional on the distribution of the neighbors of the vertex you picked. And this is a process called the Glauber dynamics. So let's see an example of this. So here I have a two-coloring of the subset of the grid. And let me pick this vertex uniformly at random. And I'll see if I want to swap it. So let me count the number of monochromatic edges that this vertex participated in without recoloring it. So I have 2 pink edges here. And if I swap it, well, actually I have 2 blue edges here. So it should be equally likely whether I keep the color the same or swap it. Okay. And each of these steps can be described by a transition matrix, 2 to the v by 2 to the v transition matrix. And the stationary distribution, meaning the distribution that this approaches as you keep running this process forever and ever, is exactly the Gibbs measure for the Ising model, mu. This is because of how we define the particular probabilities of swapping colors at each step. And what I'm interested in for analyzing dynamics in particular is this mixing time, which is the number of steps I need to do in order for the chain to be as close as I want it to be to outputting something from the stationary distribution. And in terms of measuring how close that is, I can say that's something like within epsilon of what's called total variation distance. Okay, and how is this related to algorithms? Well, notice if a Markov chain mixes rapidly, then this gives us actually an efficient way to approximately sample from the stationary distribution. How? You just start with some arbitrary two-coloring, and then you run your Markov chain for however many steps it takes for the mixing time, and then you output that sample, whatever that result is from running that many steps. And by the definition of the mixing time, that sample will be distributed approximately like what the stationary is. Okay. So this gives us an avenue towards potentially proving the existence of efficient algorithms. So you might think, okay, if I know something about the algorithmic threshold, I know something about the dynamical threshold and vice versa. It turns out that's not the case. For the Ising model, we saw that there was no algorithmic threshold. We had efficient algorithms everywhere. But in fact, for the Glauber dynamics, even if we just restrict to graphs of bounded degree, we already see the emergence of a dynamical threshold. So what does that mean? We can find some threshold with respect to the temperature so that below that temperature, we have fast mixing. In fact, n log n optimal mixing for any bounded degree graph. But when we're beyond that threshold, even if we just forget about the external field parameter entirely, we already have an instance of slow mixing, exponentially slow mixing. And the instance of exponentially slow mixing is on the random delta regular graph, which I'll talk more about in a moment. And I'll just say a little footnote. This beta U delta, this threshold, we actually saw it in Matthew's talk. This is something called the uniqueness threshold. And it's defined in the same way that Matthew defined it for the hardcore model. It's related to what's called uniqueness of Gibbs measures on the infinite tree. And I will also revisit this notion a little bit later. Okay, but instead of thinking about this result, which by the way I should credit, so Mosul and Sly gave this first result, this proof of fast mixing. Dembo and Montanari gave this example of slow mixing on the random delta regular graph. Okay, but what I really want to think about, the way I want to think about this theorem is in a picture like this. So you can think of this as sort of a phase diagram for the dynamics. What this says is that this line represents the temperature. There is some critical temperature here below which we have fast mixing for all lambda, and above which we have slow mixing for the case of lambda equals 1 on an example, the random graph. And a question this may bring up is, okay, what if we're in this regime, but lambda is not equal to 1? So now we consider adding some sort of bias towards, let's say, +1 vertices. Then can I somehow add enough bias to change the evolution of these dynamics, to change the mixing time? And I'll come back to that question later. Okay, so this was sort of just an overview of things that we know about maybe one of the one of our favorite objects in statistical physics, which is the Ising model. And now I want to go back to this particular construction I mentioned, the random delta regular graph, and say a little bit about that. But before I do, are there any questions about the Ising model?
So I have a question about,
Yeah.
I don't know if Matthew spoke a lot of
Yeah.
that, but is there, it looks, you said even that it looks very similar to the hardcore model.
Yes.
Is there a way to translate one to another?
That's a great question. So it depends on what you mean by translate. There is a way to sort of represent a lot of different models as something that is a hardcore model. It's a little bit complicated, so maybe we can talk about it later. But it's not going to be like you take the Ising model on this graph and then you get a hardcore model on the same graph. But there is a correspondence between them. Yeah.
One talks about independent sets, and another talks about colorings, and I was sort of, okay, how
Yeah. So you can sort of view colorings as independent sets in some sense, but maybe let's save that for after the talk. Yeah, it's a very interesting question. Okay, other questions? Okay. So now let me say something about the second part of my talk, which is moments, and we'll talk about the random regular graph. And so in particular, if you've been going to Rob's course, then hopefully some of this will look familiar, or maybe we'll preview what you might see later. So we've talked a lot about the Erdős-Rényi random graph, but you may not have seen this particular random graph model, which is the random delta regular graph. So let me introduce it. It's simply a uniformly random graph sampled from the set of all delta regular and vertex graphs. Great. Uniform element. Okay, compared to GNP, why should we study this? Well, one pro about this is that this delta regular graph I'll call GN delta. GN delta is like sparse, and in fact, something that we saw before, it's what we call locally tree-like. If you take a ball of finite radius in the random delta regular graph, then it basically looks like just a tree, truncated, that should be delta regular tree truncated at some finite depth. So it's got some nice local geometry that we can really take advantage of. But a con is that this distribution a priori doesn't seem easy to analyze. I'm just telling you it's a uniform distribution. So like, how can I compute probabilities and expectations with respect to that distribution? In particular, GNP is very nice in that the edges are independent of one another. So that makes it very easy to analyze and compute probabilities and moments. Maybe this distribution GN delta is a lot harder, so why should we study it? Well, one very nice thing about the random delta regular graph is actually there is sort of a more constructive combinatorial way to view this distribution, and that is through something called the configuration model. So here is how the configuration model goes. I'm going to build you a random delta regular graph. And here's what I'll do. Let me take my vertices. So let me say n is 6 and delta is 3. So 1, 2, 3, 4, 5, 6. And for each vertex, I'm going to create delta, what I'll call half edges that come out of that vertex. So I have 3 half edges coming out of each vertex. And then I'm going to pair those edges up via a uniformly random matching. So let me do yellow so it's maybe easier to see. Okay, so I'm just going to match these edges up. So maybe I'll do this. Maybe I'll do something like this. Okay, I've created a lot of loops here, maybe by accident. But the point of that is that's allowed. Okay, so what graph does this give me in the end? Okay, let's see if I can construct this graph. Let's see, I have a multi-edge here, and then I have an edge going here, and a loop. Oh, sorry, no edge there. A loop, an edge going there, and a loop. Okay, so normally you probably wouldn't get this many loops, but I'm drawing it on the fly. But the point is that the result is a delta regular multigraph, so not actually what we wanted. But it turns out this is okay because of this very nice fact, which you can take as an exercise if you would like to see a proof of this, that the random regular graph model is contiguous with respect to the configuration model. So any property that holds with high probability in this random multigraph will hold with high probability in my simple random regular graph. And so from here on out, I'm going to treat them as basically the same because all the properties that we'll care about for the random regular graph will only care about with high probability. Okay, so let's now try and do stuff on the random regular graph, in particular with respect to the Ising model. Well, what's something we can compute? Maybe the first thing we might try and compute is the expected partition function. First moments are sort of a natural first thing to try when you're on a random graph. Okay, so I'm going to try and compute the expectation of this, where g is gn delta. And I'm going to try to use linearity of expectation, right? This is a sum, so I should break it up somehow and use that sum. And so with that aim, I'm going to fix a new parameter, eta, and I'll call that the magnetization of my model. So eta is going to be the sum of all the spins, all the +1, -1 spins, divided by n. So you can think of this as a mean magnetization per vertex, but I'll just call it the magnetization. Okay, and why is this something we'd want to do? Why would we want to condition on the magnetization? So I'll write this. This is magnetization. Okay, this is nice because actually we get a lot of information just from knowing what the magnetization is. In particular, if I have a graph G, and I fix some configuration on it, and I know what its magnetization is, I get a ton more information about what's called the edge statistics of my graph. So what have I written here? I've written a 2x2 matrix that encodes the fraction of the types of edges I have in my configuration. So here in this upper corner, I have all the fraction of plus edges. Here I have the fraction of plus-minus, which should be the same as the fraction of minus-plus edges, right? Order doesn't matter. And then here I have the fraction of minus-minus edges. Okay, so if I add these all up, this should be 1. And I only had to introduce one more parameter. And I decided to introduce the parameter rho, which is the fraction of monochromatic edges. So okay, from knowing eta, you don't know just immediately what the edge statistics are, but you know it in terms of one other parameter. This is nice, because we already have lots of parameters running around. We don't need sort of more than necessary. All right, but this is what I'm going to use to try and do linearity of expectation, to try and break up my random variable into a sum of other variables. I'm going to look at the event of a particular matrix being exactly the edge statistic matrix that I wrote on the previous slide. So I'm going to give you a matrix M that's 2x2, it's symmetric, and it has the magnetizations we want. So in particular, the top row has to sum to the fraction of plus vertices, 1 plus 8 over 2, and the bottom row has to sum to the fraction of minus vertices, which are 1 minus 8 over 2. And then what's the probability that if I lay down my edges randomly for the configuration model, I get exactly that matrix? Okay, so this is the only computation that I'm going to do throughout the whole talk, and it will, as you see, take up the entire slide, but then the slide will be over. But you can view this as, if you're just learning about first moments and you're sort of early or new to combinatorics, then this entire slide you should view as an exercise in counting. Okay, so the first thing I'm going to claim is that if my magnetization is eta, and I remember I have delta n vertices now, I don't have just n because I'm in the configuration model, then 1 plus eta over 2 times delta n is the number of vertices I have with a +1 spin. And this is the number of vertices I have with a -1 spin, right? That's simply because of the definition of magnetization, and the plus and minus spins, they have to sum to delta n. Okay, so what does that mean? Let me try and lay down my uniform random matching. Well, first of all, let me choose which +1/2 edges I have to participate in the bichromatic edges. So let's think about building my graph. Let's say these are the +1 vertices, and these are the -1 vertices. And so I have 1 plus eta over 2 delta n of these. and I have 1 minus eta over 2 delta n of these. And let me first choose which half edges come out here and which half edges come out here. Okay? Well, how many ways are there to choose these? Well, my matrix told me there have to be m plus minus fraction of edges in total that are these edges over here. So I have this many choose m plus minus delta n ways to pick this side of the edges. And similarly, I have this many choose m minus plus, which is the same as m plus minus, ways to choose this fraction of edges over here. So these are how I'm going to choose sort of the endpoints of my bichromatic edges. Yeah?
So just check out that these vertices are corresponding to the half edges.
Yes, exactly. Yeah. Yeah, so I could, for example, have one vertex with multiple half edges.
But they're delta n. Are you saying on the vertices corresponding?
Yes, good point. Okay, I shouldn't have written vertices. Thank you, Rob. These are +1 half edges. Yeah, so for example, I'm thinking of a vertex having a +1, and I'm thinking of like all of the delta half edges that are coming out of that, and I'm thinking of these as the +1 half edges. Yeah, good point.
Thinking the partitions are fixed at +-1.
Exactly, yes. I'm fixing my configuration first, my assignments of +-1s, and then I'm choosing how to put my edges. Yeah, exactly. Okay. Other questions? Yeah, that was good to clarify. Okay, so then I've chosen my half edges, and then how do I just pair these up, right? I have a bunch of +1 and -1 half edges that have to pair up with one another, but they could pair up in any way they want. And so I have, I can think of like fixing and ordering for the +1 half edges and then permuting the -1 half edges to match up with those. So I have however many half edges there are, m plus minus times delta n, factorial ways to match all of these, right? So I could do something like this. Oh, I didn't. I need one more edge. Something like that. Okay, so now I've placed all of my bichromatic edges. Now, how do I place the rest of my edges in my random graph? Well, I just need to match up everything that's inside here and everything that's inside here. Okay? And so we know how many ways there are to put a perfect matching down on a given number of vertices. And so it's this double factorial expression, m plus plus delta n minus 1 double factorial ways to perfectly match everything that's in here to be a plus edge. So I have some matching in there. And then similarly, I have that many ways to put a perfect matching in the other side. Okay, yeah?
So I always forget what double factorial is. It's not factorial.
It's not factorial. It's like a factorial over a factorial, yeah.
It's small, the factorial. It's like the worst notation in the world.
Yeah, I have to say I also don't remember exactly the expression for double factorial. I just know that it counts the number of perfect matchings. But this is something one could look up. Other questions that I can't answer? Okay, exercise. Figure out what double factorial means. Okay, so that's all the computations that I'll do. Okay, so given an edge statistic matrix, like a potential edge statistic matrix, what's the probability? It is exactly the matrix of my random graph. It's like the product of all of those terms that we had on the previous slide, and then divided by the total number of ways to match up all of the edges, which is, again, this mysterious double factorial. Okay, and then if I want the weight of all configurations with magnetization eta, then I simply sum over all m this probability times the weight that I get from my Gibbs measure, this e to the beta times this expression, the number of monochromatic edges. There's an over 2, and I think there shouldn't be. Yeah, I think there shouldn't be. It's already a typo. And this lambda factor. And those should be delta n's as well, not n's. Okay, there's some typos in there. But the point is that we have this combinatorial expression, we can sum it up, and it's some sum over these m's with an eta in it. All right, this is not exactly, we're not done yet, right? We fixed the magnetization, and now we have to sum over all magnetizations, but actually I'm going to stop here. Because one thing to note is that this expression itself, this z, g, n delta, where I'm fixing eta, this is a partition function, right? But not of the Ising model. It's of what I call the fixed magnetization Ising model, where I only look at the configurations where I have specified a number of +1 vertices, and I said I'm only considering those. And you can consider the Ising model on that by just like conditioning your measure mu on having that particular magnetization. Okay, but there's some more algebra in here where you can use Stirling's formula and rewrite things in terms of binomial entropy, and you do a lot of fussing around. And if you take the limit of this as n goes to infinity, what will happen is that this sum is dominated by its maximum term, so maximum over all m. And the function that you get will actually have a unique maximum for a given eta. So we can actually rewrite this as a function of just eta once we've fixed like the other parameters, delta, beta, lambda. So that's what I'm going to do. I'm going to do a little other stuff first. I'm going to take a log just so I can focus solely on the exponent, because this will be an exponential thing. And I'm going to divide by n, because every term will have n. And I'll write this as a function of just eta, where I fix all the other parameters. And now let's see, what does this look like? What is this expression, actually? So here I've given you a plot of it. I've picked delta equals 4. I've picked beta to be a little bit bigger than this beta u, this threshold. And on the left, I've picked lambda to be bigger than some lambda u I have not told you about yet. And on the right, I've picked lambda to be smaller than whatever this lambda u is. Okay, and what's something you can observe about these plots? They look kind of similar, but they also look very different. Okay, in what ways are they similar? They seem to have kind of similar shapes. But this one has one single global maximum, and it's actually, you might not be able to tell, it's increasing up to that global maximum, and then it dips. Whereas this one has a global maximum, but it also has a local maximum, and therefore a local minimum in between them. So what is this telling us? Well, we can think of the global maximum as telling us which configurations dominate our partition function, right? It's saying this is the contribution of configurations at a given eta. And the ones at this particular eta take up the most space, have the most weight. And on the left side, that's sort of a unique property of the contributions from this eta. And on the right side, we have this global maximum, but we also have some configurations that contribute a lot, but just not as much. Okay. So this is an interesting phenomenon, and actually we can understand where these points are. So these critical points are in one-to-one correspondence with certain Gibbs measures on the infinite, that should be delta, delta regular tree. So now I'm going to take a little sidebar and say like one slide's worth of things about what this means, and it will look reminiscent of what Matthew discussed yesterday about the infinite tree, and then we'll go back to analyzing this plot. But first, let me tell you a little bit more about what this means. Okay, so the infinite tree, we saw it yesterday. One way to define the Ising model, it's not clear how to just define an Ising model on an infinite graph. You can't count the number of monochromatic edges on it. So one way to define an Ising model, the Gibbs measure on an infinite graph, is to take a limit of some measures on finite graphs. And for the tree, we can do that by taking the limit of Gibbs measures on finite depth truncations of the infinite tree. But the thing is that we need to also specify the boundary conditions. So if I take my tree, and I sort of do it down to some depth, L, then this Gibbs measure, I can specify what the spins are at the leaves. So for example, I could do all pluses. And that would induce a certain measure on this finite graph. And let's say I do that for every depth L, and I take that as L goes to infinity. But I could potentially do another set of boundary conditions. For example, I could do all minus boundary conditions. And the question is, do these give the same limit? Right? Do I get the same measure as I take the limit as L goes to infinity? And it turns out the answer is not always. Sometimes it does, but sometimes it doesn't. So these uniqueness thresholds that I haven't told you about yet, beta U and lambda U, they're defined as the thresholds for which this question, the answer to this question changes, whether we have a unique infinite volume Gibbs measure and whether we have multiple. And where we're working, the two pictures I showed you, the one on the right with the 3 critical points, that was taking lambda and beta in the non-uniqueness regime. And in particular, these 3 critical points correspond to 3 different Gibbs measures. Mu plus, which is actually the one with all the plus boundary conditions, mu minus, which is the one with minus boundary conditions, and nu, which I'm not going to tell you anything about. Okay, and here's sort of a concrete relationship between like this fixed magnetization measure with the eta and these Gibbs measures. So what this says is that if I pick some eta, so I fix beta, if I pick some eta, then what I can do is I can find a Gibbs measure, mu, with some parameter lambda that's in this set mu plus, mu minus, nu, such that the expected spin at the root is exactly eta. Okay. What does that mean in terms of my plot? It means that if I pick an eta that's not exactly at one of these critical points, I can pick a different lambda. And a different lambda will give me a different plot, right? And I can pick lambda to shift my chosen eta to one of these critical points. And the correspondence between the eta and the lambda will be the expected spin at the root. Okay, so one question you can ask is there something stronger you can say about this correspondence between a measure, the fixed magnetization measure on the random graph, and these weird measures that are on the infinite tree? And hopefully yes. My answer is hopefully yes, but this is ongoing work with Reza Gaysari and Will Perkins to analyze something that we call local weak convergence of these measures on the graph to the corresponding measures on the tree. Okay, so in the last 15 minutes that I have, I will get to the last part of the talk, thankfully, which is mixing. So let's go back to this picture and actually discover like what can we use all of this information that we learned about the random regular graph to say about new things. And in particular, we'll go back to the Glauber dynamics. Okay, so let's look at this picture again, and really we'll focus on this one on the right. What new can we learn from this picture? How else can we interpret this? Well, one thing we can learn is what I said about these weight contributions of different configurations, right? Remember I said these configurations look like they sort of dominate the partition function, but these are kind of subdominant. They are like not the dominant ones, but they contribute a lot. And if you've seen Markov chains before, this might remind you of something that has to do with mixing time, in particular bottlenecks. Because in order to get from the states here to the states here, we have to go through this valley, which has very, very small weight, and so would be highly unlikely to go through. So what is a bottleneck? Here's a great illustration of a bottleneck. I'm looking at basically my configuration space, and I have a bottleneck if I can find a chunk of my configuration space that's not too small, and I can find another chunk that's also not too small, and I have like an exponentially smaller chunk that connects the two. So in order to get from any state in S2 to any state in S1, I have to be forced to go through S3. And that is something that will cause a Markov chain to mix slowly, because if you imagine sort of taking these local steps to get from configurations in S2, then I have to be able to go through these ones in S3. So the larger piece I'll refer to as stable or dominant states, and the smaller piece I'll refer to as metastable states. Okay, so here we actually have a good candidate set of stable and metastable states. These should be my stable ones, and these should be my metastable ones. Great, and actually based on what I've described to you, we're done, right? We've proven this already. Okay, but we haven't. And maybe you've already seen this sort of thing in Rob's courses, or you will. This was only a first moment, right? I only showed you the expected partition function. That's what this picture is. I haven't shown you that this picture is actually the truth, or that it holds with high probability. And that's really what we need in order to show that this bottleneck actually exists. But what we do is we actually show that that this is the truth. The partition function lies between some simple expressions involving the first moment. And so the proof of this, the upper bound is the first moment method. We use Markov's inequality, so that's quote unquote easy. The lower bound is the second moment method, and historically this is harder, and in fact it was harder for our case. We not only had to do a second moment method, we had to go to some particular planted model and then do a second moment method there, and we really had to use this relationship between the random regular graph and the infinite regular tree that I'm not really telling you much more about. So sort of disguised in this lower bound is most of the work. Okay, but what are we able to show? So this is work with Aya, Marcus, and Will. What we showed is that the Glauber dynamics are slow mixing in some range that goes all the way up to this uniqueness threshold. So this is that barrier for there being 3 critical points in this plot that I showed you. And I've plotted log lambda instead of lambda, so the case that was known is this is the x-axis here. So we had already shown for lambda equals 1 that we knew the slow mixing on the random regular graph. We've extended those results up to this regime. And there's a complementary set of results that knows fast mixing in the uniqueness regime and down to this other threshold lambda a. Okay. So that's what we showed, but that actually isn't what we set out to show in this work. So in the last amount of time I have, I'll tell you another setting where we considered this type of problem and with the same setup and how we were able to prove some new things there. Okay, any questions? Yeah, Rob.
Sorry, is this picture just for random regular graphs?
Yes, this is just for random regular graph. Yeah. Yeah. Other questions? Okay. So let me say some other new things that we said, which was about this fixed magnetization model. So I mentioned that this partition function that we plotted, it is a partition function of a different model where we condition on having a particular magnetization. And so we can formally define that model. I'll call the measure mu hat. And it's simply mu conditioned on having the desired number of +1 spins. And you can see that the expression looks similar, but actually this lambda term has completely disappeared. I don't have to ignore it. It's disappeared because the exponent of lambda was a number of +1 spins, but all of our configurations have the same number of +1 spins, so I can forget about it. Okay, and this is quite a different model. So in particular, like the structure of this model is different than for the regular external field Ising model. Remember, at low temperatures, so at high beta, we said that we're biasing towards having all monochromatic configurations, because those were the ones with the most weight. Now, we can't have all monochromatic configurations unless we set our magnetization to be all of the graph. And so already the structural question is a bit different. And it turns out the algorithmic question is also has a different answer. So for the Ising model, there were efficient algorithms everywhere for all graphs. What we now know, based on work of Carlson, Davies, Kola, and Perkins, is that even if we just look at bounded degree graphs, we have a computational threshold. And this is the same beta u I showed you before, and now we have a different curve, eta. So instead of plotting lambda, I'm plotting eta in terms of beta. And there is this region where there exist efficient algorithms, but there's a different region for magnetizations close enough to 0 where I have NP hardness for this problem. So already we get quite a different landscape. Okay, and this is the theorem that they showed, so just in words. And let me note that although this may be surprising, for people who thought the Ising model should generalize to the fixed magnetization Ising model, it's not surprising in terms of there existing a computational threshold. Other models exhibit computational thresholds. For example, something called the antiferromagnetic Ising model, where you allow beta to be negative instead of positive, and something called the fixed size independent set model. So this is the hardcore model that was mentioned yesterday, but now we, again, fix the size of the independent sets we're considering. So we're conditioning that measure. Okay. So interesting things are happening here. Let's take a look at the dynamics. So one thing we could do is let's just try and define Glauber dynamics for this new model. I'll take an arbitrary coloring. I'll pick a random vertex and I'll flip its color. Except I can't do that because if I flip a color, then I'm changing the number of +1 spins that I have in the graph. Okay, so what's the next best thing? I pick two opposite colored vertices and I swap their spins, or I don't. And the probability that I swap or don't is conditional on the weight of the configurations. And this is a process called the Kawasaki dynamics. So let's just see an example of that. I pick two vertices that are opposite colors uniformly at random. So let me count sort of the weight contributed by these vertices. I have one blue edge here, and I have two pink edges here, so I have three monochromatic edges involving these. And if I swap them, I have three pink edges here and one blue edge, so I have four monochromatic edges. So I should be more likely to swap them than not swap them. And the probability I use is exactly the proportion of the weights. Okay, and this process will, by the way I've defined it, actually converge to this fixed magnetization measure, mu hat. And we can ask the question, what is the mixing time? Okay, so in this paper that analyzed the computational threshold, they conjectured that the computational threshold is also the dynamical threshold. And that's a very natural conjecture to make, because in this previous work by Jane, Michelin, Huy Pham, and Vuong, they showed that this exact statement is true for the fixed size independent set model. That if you define some dynamics on the hardcore model, the thresholds coincide. Okay. So what we did is we disproved this conjecture. Well, we proved and disproved it. So this beta u does still mark a dynamical threshold, but in terms of the eta, when we're beyond beta u, we have two new thresholds. Okay. So what we proved in our work is both fast mixing and on all bounded degree graphs, and we proved slow mixing on an infinite family of regular graphs. Okay. So let me just point out some things to observe about this phase diagram. So one thing that surprised us is the fact that this eta u and this eta c are not the same. What this tells us is that there is this region of magnetizations between eta c and eta u where there exist efficient algorithms to sample, and the ones in the previous paper, rejection sampling, they provide an efficient algorithm. But this Kawasaki dynamics, they're not an efficient algorithm. They mix slowly. Another thing that surprised us is this emergence of this gap. It's the same gap that was in the Glauber dynamics picture, which I didn't address, and I'll address both now. We don't know what happens in this white region. Our fast mixing techniques only extend up to this red eta A curve. A stands for analytics, so this has something to do with zero freeness of the partition function. And eta u is this uniqueness curve. And it's known that eta A and eta u are not the same. And in fact, we actually don't know what eta A is. I wrote eta A bar because we only know an upper bound for eta A. We don't actually know an explicit expression for it. So there's this mystery happening here. And one last thing I'll say about the slow mixing is sort of why does this plot look similar to the Glauber dynamics? Because the same proof sort of attacks both of them. The slow mixing construction is actually a construction consisting of several disjoint copies of random regular graphs. And what happens is that you can sort of tune the magnetization on each copy, but you can't, try and fix those magnetizations independently of one another. Because overall, your magnetization has to be eta. So I have many copies of Gn delta. And I set some copies to have this eta plus magnetization, that global max on the picture of F. And I set some copies to have eta minus magnetization. But overall, we have magnetization eta. So they do need to average out. And then what happens is I can't, in order to get to sort of the dominant state that I want to be on this graph, I have to sort of fix the copies in sync, and I have to go through these exponentially unlikely bottlenecks. So in particular, this construction is interesting because we actually know that on a single copy of the random regular graph, we do have fast mixing in a region that overlaps with our slow mixing region. So there's some region where many, many copies of the random regular graph give slow mixing, but one copy of the random regular graph gives fast mixing. So what's happening here? For example, what happens with 2 copies of the random regular graph? Sort of unclear to me. OK, so I think that is all I wanted to say, so I'll end there. Thanks for your time.